Welcome to geometry class. Let's talk about isosceles and equilateral triangles. Before we do that, let's just review what an isosceles triangle is. First of all, an isosceles triangle is a triangle with at least two congruent sides. So if I'm talking about a triangle, I want to be able to answer the question, is it isosceles? I'm simply looking to identify whether there are two congruent sides, at least two congruent sides. Notice that just because there are more than two congruent sides, for instance, if I'm dealing with an equilateral triangle, that doesn't mean it's not an isosceles triangle. It still is. This is a different category of isosceles triangle. So at least two congruent sides is what we're looking for if we're trying to identify isosceles triangle. Those sides, the congruent sides, are called legs, and the third side is called the base. We also have special names for the angles in an isosceles triangle. The angle that's common to the two congruent sides is called the vertex angle, and the other two angles are called base angles. Let's take a look at that. This diagram here, I'll indicate that this is in fact an isosceles triangle by showing that those two sides are congruent. If those are the congruent sides, then this is the vertex. That's the vertex. And these two angles down here, those are called the base angles. Vertex and the base angles. Notice these two sides are legs. This side here and this side over here. And this is called the base. You'll notice that the base is always included by the base angles, and the vertex is always included by the legs. Isosceles triangles are common in the world. You see them all over the place. It's very common to see them in buildings and in bridges. Let's take a look at just a few examples. This is actually the very top of the Washington Monument in Washington, D.C., and you can see there are some gentlemen working here. These guys were sent up there to make repairs to the Washington Monument after a recent earthquake damaged it. It is reopened now, actually. But you'll notice if you look at this top, it is an isosceles triangle. And you can see that these legs are congruent. So that's one example. This here actually shows a crane. Here's a crane back here, structure of the crane. And it has a cable down here, onto a block. And you can see what looks like an isosceles triangle in here. These are two legs of the cable, sometimes they're actually called, down to a steel spreader beam or support beam. And you can see it looks like an isosceles triangle. The question is, do we see any other isosceles triangles in the picture? The truth is there are actually quite a number of them. If you look over at the boom on the crane, there are all kinds of isosceles triangles in here. And you can see them. They're a little bit hard to spot because of the fact that there are multiple sides here. We're sort of looking through two different layers of isosceles triangles, but you can see quite a lot of them in there. Lots of isosceles triangles. Here's a bridge. You can see isosceles triangles here. There's one right there, another one, and then there's one right here as well. Let me point out one thing right here, specifically about this triangle here. There's this sort of there's this tendency to think of the word base as meaning the bottom, but it doesn't mean that at all. Remember, the base is the side in an isosceles triangle that is included by the two congruent angles. So this is actually the base up here, whereas this down here is the vertex. Remember, in geometry, there's really no up, down, left, right. So make sure you don't get confused about that. If the triangle has the vertex pointing down, that must mean the base is up. We'll look at some isosceles triangle theorems, and we'll work through some short proofs on these. Here's the first one. The isosceles triangle theorem says, if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So if I have two sides that are congruent, the theorem allows me to conclude that these base angles, the angles opposite those sides, are also congruent. What that means, to state it differently, is that in every isosceles triangle, the base angles are congruent. Let's see if we can prove that real quick. We'll start with a triangle. And we know, for starters, that the hypothesis is true, right? Two sides are congruent. Let's see if we can prove that the base angles, these angles down here, are also congruent. In order to do that, I'm going to go ahead and draw in the angle bisector from the vertex. And if that's the angle bisector, then these angles, by definition, must be congruent. Okay? And you'll see what we have here. We have two triangles. I'll call this triangle number 1, which is not the way we normally name them, but for expedience sake, and triangle number 2. Notice I have side, right? We've got side. And then we have angle. and then we have a common side right here, right? That's side angle side. And so by side angle side, we find that these two triangles, triangle 1 and triangle 2, are congruent. Well, if those two triangles are congruent, then every part of them must be congruent, every corresponding part, including this angle and this angle. Since those are corresponding parts, they must be congruent. There's a rule that I will refer to very frequently. It's known as CPCTC. And it stands for, and you should put this in your notes, corresponding parts of congruent triangles are congruent. So in order to prove these angles congruent, the way that I did that was I first simply proved that these two triangles were congruent. Once I proved that the triangles were congruent, I know that all their corresponding parts are congruent as well. So that is the proof of the isosceles triangle theorem. Next theorem is called the converse of the isosceles triangle theorem. It says if two angles of a triangle are congruent, the sides opposite the angles are congruent. Suppose that instead of knowing that these sides are congruent, instead of knowing that, we know only that these base angles are congruent. Can we conclude that these sides, this side on the right and this side on the left, can we conclude that those are also congruent? Notice that those sides are opposite the angles. Let's go ahead and, again, draw in the angle bisector here. And when we do that, of course, we know we have an angle here that is congruent to an angle here by the definition of bisector. Okay? And we can look at this again and say, well, what do we know in here? Well, we have angle. These two angles give us angle congruence. And we have a second pair of angles. And we also have side. Okay? So we have angle, angle, side in this case. And you'll notice that it is the corresponding side with respect to those two angles. Angle, angle, side. So by angle, angle, side, we know that these two triangles, and I'll label them this time, triangle A, B, C, and triangle D, B, C. Those two triangles are congruent by angle, angle, side. And if they're congruent, then CPCTC applies. Corresponding parts of congruent triangles are congruent. Therefore, this must be congruent to this. And we've proven the converse of the isosceles triangle theorem. The next theorem is called the isosceles triangle bisector theorem. It says the bisector of the vertex angle of an isosceles triangle is the perpendicular bisector of the base. So we have here a diagram of an isosceles triangle. Let's just make sure it's an isosceles triangle. There it is. Okay. And we're talking about the bisector of the vertex. That is the bisector of the vertex right there. And what we want to know is whether the following two pieces of information are true. Number one, is this segment congruent to this segment? If it is, that will mean that this line right here, line AB, as I will call it now, if these two segments are congruent, then line AB is a bisector of side CD. So that's the first thing we want to know. And the second thing we'd like to know is, does this segment AB intersect CD at a right angle? That's the two questions. If we can answer both of those questions in the affirmative, then we will have proven that this angle bisector is also the perpendicular bisector of the base. Let's see if we can do that. Right, so here we have the angle bisector drawn in, and you can see we have triangle CAB and we have triangle DAB. In order to prove this last theorem, we will attempt to first show that these two triangles are congruent, that is triangle CAB and triangle DAB. Well, I think you can see that we have side and we have angle, and by the reflexive property we have side, because of course segment AB is congruent to segment AB. So we have side angle side congruence, which means that triangle CAB is congruent to triangle DAB. Therefore, we can conclude by CPCTC, corresponding parts of congruent triangles are congruent. CB must be congruent to DB because those are corresponding parts in two congruent triangles. And we can also conclude that the measure of angle ABD, this angle, must be congruent to the measure of angle ABC, this angle, because those are also corresponding parts. We'll also note that this is a linear pair. And of course, the sum of those two angles, which is, we could name x and x, or assign variables x and x. X plus x must equal 180 because it's a linear pair. So 2x is equal to 180. So therefore, x is equal to 90. So we are absolutely certain that this is a right angle now. In fact, we have 2 right angles. Okay, so we've just proven that third theorem. Let's just take a moment now and look at a couple examples. Suppose I had this isosceles triangle, and let's suppose also that I knew the measure of this angle were 70 degrees, and I wanted to find the measure of this angle up here. How could I find it? Well, the first thing I'd need to know is the first thing I'd begin to think is when I look at this, I'm thinking of the triangle angle sum theorem that says that the measures of the interior angles of a triangle add up to 180 degrees. The problem here is I only have 2 of the angles. So if I were to begin to write the equation x plus 70 plus the third angle, which is unknown, equals 180, I am then faced with this dilemma where I have to know that third angle. But the isosceles triangle theorem says that if 2 sides of a triangle are congruent, then the angles opposite those sides are also congruent, which means the base angles here equal 70 degrees. So now I have that missing part, 70 degrees. Then we just solve this with algebra. X plus 140 equals 180, and x therefore equals 40. And so we can find x. Now, that's a pretty typical problem. Suppose we had a different but related problem that said this was 65 degrees, and this was 65 degrees. And let's just call this triangle ABC. And suppose we knew that this was 17.5 inches, and I'm asking what is AB? AB equals what? What is the measure of segment AB? Well, all we need to do here is apply the converse of the isosceles triangle theorem. Since we have 2 angles that are the same, we know that the sides opposite those angles must be congruent, and so therefore this is 17.5 inches as well. One last look at one of the theorems. So we have an isosceles triangle. We'll just go ahead and state that. And suppose that we have identified this as the angle bisector. And suppose that we have the points A, B, and C. And let's further suppose that we know the measure of angle B to be 70 degrees. And I'd like to find the measure of angle CAB. Find the measure of angle CAB. How do we find it? Well, again, we have this triangle CAB, and we know that the sum of the interior angles of that triangle are 180. But of course, we have 2 missing angles. We need to find the measure of angle CAB, but we don't yet know the measure of angle BCA. Well, because it's an isosceles triangle, we know that the angle bisector of the vertex is also the perpendicular bisector of the base. And so we can be sure that's 90 degrees. Therefore, the measure of angle CAB must be 20 degrees. It's the complement to angle B. Another type of problem we might see in applying that third theorem is that perhaps we know that this segment DC is equal to 10 units. And maybe we're asked the question, well, what's the length of segment BC? Oh, it must be 10 units as well, because this is the perpendicular bisector of the base. Now we need to look at a few rules that are called corollaries. And a corollary is a statement that follows immediately from a theorem. You may remember I have frequently described theorems as shortcuts. And if I could say this, a corollary is basically a shortcut to a shortcut. So it's new shortcuts that flow directly from shortcuts we've already learned. So corollaries. Here's the corollary to the isosceles triangle theorem. It says if a triangle is equilateral, then the triangle is equiangular. Let's take a look at that real quick. Suppose I have a triangle, and let's suppose that the triangle is called ABC. And let's further suppose that we know the triangle is equilateral. We're asking the question, is it also equiangular, and if so, how can we prove it? The way that we work through this corollary, or the proof of the corollary, is to focus on 2 sides at a time. We'll call those legs, and we'll let the third side play the role of the base momentarily. So for instance, if we look at side AB and side BC, with side AC as the base, side AB and side BC, well, we know that since they're congruent, then opposite angles must be congruent, which means angle A is congruent to angle C. Now we shift our focus, and instead we look at sides AC and BC. When we do that, we find again that the angles opposite those sides are congruent. And so we find that angle B is congruent to angle A is congruent to angle C, and we've proven the corollary. Let's take a look at the corollary to the converse of the isosceles triangle theorem. Because if a triangle is equiangular, then the triangle is equilateral. Quick look at that. So assuming we have a triangle like this, and let's just go ahead and state that it is equiangular, like that. We're asking the question, is it also equilateral? Well, we know that if two angles in a triangle are congruent, such as angles A and B, then the sides opposite those angles are also congruent. So this side BC is congruent to side AC. If we then shift our attention to angle C and angle B, we know that the sides opposite those angles are also congruent. And so this segment AB must be congruent to segment AC. And you can see now that this must be an equilateral triangle. So that's the proof of the second corollary. Those are the rules relating to isosceles and equilateral triangles. Make sure you complete a few practice exercises to check your understanding and to ensure you're confident in these problems. If you have any questions, send me an email.